Hello and welcome back to Let's Code Physics. We are continuing to develop our pendulum model. We already saw some interesting stuff last time where this graph gets distinctly away from a sine or cosine shape. We haven't really tried too much playing around yet with the initial speed of the pendulum. So let's see what happens when we give this thing an initial speed. Let's see if we can get it to circle its way around. Okay, nope, it is still falling back down. Let's see what happens if I increase the initial theta dot. Okay, it is exceeding its original by a little bit. Let's see here. Let's go ahead and bump it up to 5. Why not? Because it does incorporate theta dot from the beginning there. Okay. Oh, cool. So now it's just spinning. And so this thing definitely not a sine curve. Not stopping anytime soon. That's actually a little bit fast. Why don't we slow that down a little bit here? 5. There we go. Zoom, zoom. Yeah, so this thing's got a little bit of a curve to it. That's kind of cool. So yeah, there's some neat stuff that you can do with pendulums. Let's see. One of the features we have not added in yet is the damping coefficient. So let's see what happens. Actually, let's take that previous case where the pendulum has an overabundance of energy at the beginning. Let's see what happens when we add in some damping to it. So here we've got the overabundance of energy. It is circling back around, but eventually that damping force will come in and let it not be able to make it back over the top. There we go. So we got this cool behavior over there. And oh yeah, so now it's rotating backgrounds. Okay, so the reason this thing was keep on increasing because this thing doesn't have a sense of giving it the modulus of the angle with respect to 2 pi. So this gives you an idea of how many rotations it went through. That's kind of cool. And of course, eventually the damping causes the oscillations to die off. Here we end up with back to what we had at the beginning of the first video, which is kind of cool. So you end up with some neat stuff. Let's put theta dot initial back down. There we go. So you end up with some pretty neat stuff. But even when you add in the damping force, it doesn't really change the behavior all that much. I mean, you get this behavior back, right? But you don't necessarily get something that's significantly different from a sine curve, right? I mean, it's still a sine or cosine like, it's just got a decreasing amplitude. So where you can get the really interesting stuff is when you start bringing in a driving force. So for example, if you make a driving force of let's say cosine of let's make it 0.1 times t, right? Because if I put this thing low, that means it has a low frequency. Let's see what that does. Oops, and I didn't call it t, I called it time earlier, right? I spelled everything out so that I could remember what it was. And what you end up with here is, again, similar behavior, but eventually that driving force is going to be what eventually takes over the pendulum. So you end up with its period, not the previous period. So this thing's period is, let's see, 2 pi, we've got 0.1 is 2 pi over t. So t should be 2 pi over 0.1. So you see it's leveling out here. Let's see, 2 pi over 0.1, so that should be 6, right? So if I go from here, that's 30, and I go to here, go to the next one, 34. Yeah, so it's getting closer to that driving period of about 6. Actually, why don't we make it to where we calculate a period here. Let's give an explicit period of 10. And so then this thing can be 2 pi divided by the period. There we go. So this thing should end up with a period of 10 eventually. Obviously right now it doesn't have a period of 10. It's got something close to its original period. But as the driving force acts, this period should end up matching that on the graph. Let's see. So I just discovered something cool. I clicked inside the graph window, and the cursor is moving as the graph develops, which is pretty cool. So this thing's got 14.58. This thing's got, okay, so we haven't gotten that yet. It's also possible I'm mistaken about the eventual behavior, although this thing is not, hasn't leveled out to a single sine or cosine yet. That's interesting. So let's see. Yes, this is interesting. Or maybe it's the overall period. Yeah. Maybe you have to look for the... Okay, so this is interesting. So this piece is a little bit lopsided. This piece has become kind of symmetric. I wonder if we'll get something more symmetric here. Nope. All right, what about this? What about the period from this peak to the next one? That's right about 50. This is right about 60. Okay, so here's where... Okay, I was right. So the driving period eventually takes over. So this peak is at about 50. This one's about 60. This one's going to be about 70. Boom, there you go. Okay, yeah, so initially the sort of natural frequency goes away and it's replaced by the driving frequency, which is pretty neat because it means that you can set the pendulum's driving frequency and eventually the noise goes away. So after about, assuming we're working in meters and seconds here, so after about a minute of running the experiment. Although, again, you notice these things not really... I've not yet figured out how to scroll within this thing. I don't think you can. As you can see, though, this thing eventually does get to something like simple harmonic motion, but this is definitely not a sine curve. I mean, a sine curve never does that. This is kind of too straight to be as... Well, I guess this might be closer to a cosine curve, since that's what the driving force is. So that's kind of cool. And let's see, if we increase the period, those things will become broader, right? So if I make this a 20, then those bumps will become broader. I suppose I could decrease some of this original stuff by decreasing the original theta. Let's say theta only starts out at 1 instead. Give it a little bit less energy to have to dissipate before the driving force really takes over. And of course, changing that amplitude doesn't change. It gets a period closer back to pi there, like we had before. Now it's interesting. You watch this one. It looks like the pendulum is dying, and then suddenly its motion, it gets kicked by the driving motor here. I suppose what would be helpful visually would be to have some kind of animation of the driving force, maybe. Yeah, I could. Is there a way I could do that? I'll have to think about that. I'll have to think about if there's a way I can animate the driving force on here. Yeah, so again, you see the original initial motion is dying down, and this thing is, driving force is coming in. So it should have a period of about 20. So here's 50. So the next minimum should be at about 70. Right there, 70. There you go. So it's still got this other waveform superimposed on it, but that's dying down because of the damping force. Another way we could get that to come in sooner would be to increase the damping coefficient. So here we'll see that initial oscillation die down a lot faster. Oh, I think I'm going to turn on this thing's transparency to make sure we remember it's a reference line. Okay, yeah, so here we go. So those oscillations die down a bit faster. We're about to reach a maximum, it looks like. We got a max at 20. Let's see if we get a min at 40, as we would expect. Come on. Oh, we get a min at 30. Oh, no, sorry. Yeah. We should get the next max at 40. Sorry. I tell my students every semester the period is peak to peak, and I'm not telling them to remind them. I'm telling them to remind me. Cool. So that's working out well. That's good. Let's see the reference line. Let's make this thing's transparency equals 0.5. Wait, is it transparency or is it opacity? Let's find out. It is not transparency. Okay. Unless that thing is... No, that looks pretty opaque to me. Okay, I want this thing to have an opacity of 0.5. There we go. That's a bit better. Now we can remember that that's a reference line. In fact, let's even bump that down by another 50%. Cool. And actually, while we're tinkering, let's up the rate, because now we're more interested in the graph than we are in the animation. So the way to visualize this driving force is that you've got some knob right here that is attached to a motor, and it's rotating according to the driving force, and that's why you get that weird stuff going on there, because it's trying to follow the motor. And here we get the driving force behavior pretty quickly. So we go from 60 to 80 to 100. So that's pretty cool. Of course, and the fun part comes in when you have a non-linear, not non-linear, a non-sinusoidal driving force. So for example, suppose instead of that, suppose we had, that would be a fun one to try. Let's do this. Let's try a periodic push. So this would be like if you have a kid on a swing, you give it a periodic push. So let's do it this way. Let's say we're pushing every 2 seconds, maybe. And so what you can do is you can say that FD equals, let's do this. What I want to do is I want it to be that every 2 seconds, I want it to be that every 2 seconds it gets a push. So let's see. I need to say FD equals, and let's give it a push. Let's see. This has been a maximum of 1, so let's set the push value to be 1. Here's how we'll set that up. Is we want to check the modulus between the amount of time that has passed and the driving period here. Does this thing know modulus? Modulus. All right, let me look up how to do modulus in Python, and I'll be right back. Maybe it's the percent sign. Is it the percent sign? Modulus Python. Oh, it is a percent sign. Okay. Not mod. So if time percent 2.0, right? So what modulus does is it takes the one thing, divides it by this one, and it gives you the remainder, right? So it's the same, actually it should be period, right? Right, so it's the same thing as when you're in 3rd grade and you first learned division and they had a remainder pop out instead of having you calculate a decimal. Maybe you all used calculators in 3rd grade. I don't know, but that's what we had to do. So let's say if that is, we want it to be kind of close to it. Like it's obviously not going to equal 2 and 4 and 6 and 8. But let's say if the remainder is less than 0.1, so it's within a couple of ticks of the push. And actually, let's make this the absolute value. There we go. So if we're within the window of the push, you give it this force. Else FD is equal to 0. Does else get a colon? I don't think so. Let's find out. Invalid syntax, apparently. Else does get a colon. All right. Okay, cool. So you can see the push coming in every second. So let's see here. There's one at 20, and there's one at 22. Okay, I need to decrease my Tmax. I increased it for the intro, and now I'm regretting it. So let's see here. Tmax, yeah, not 150. You only need to go out to like 20, buddy. Okay. I just wanted to have it animating while I gave the intro, Okay, cool. So we have the initial motion dying down. We're starting to get the push. So there's one at 15. There's one at 18. It's a bit weird because I'm expecting it. Oh, it is supposed to be every 2 seconds. Excuse me. So maybe that is about right. So let's do this. Let's make the push a little bit more dramatic. Because the natural frequency is going to be about 1. So I'm making this one about... Okay, so I am making this one a multiple of the original frequency. So let's make this one 2.5. So we'll make it every 2.5 seconds you get a push. And let's actually up the value of this because it's having trouble overcoming the damping coefficient. Let's see here. Okay, cool. So this, you're getting a push every 2.5 seconds. So let's see what happens here. So let's see. Okay, so it happens at, let's figure out when it's happening. It's happening at every 5, right? So it's happening at 5, 10, 15, 20. So it's happening at 10. So this is what one push looks like, is at 10 seconds. And then I should expect another one at 12.5. And lo and behold, there's another one at 12.5. Okay, so I get these little kinks. So the next one should be at 15. Is that going to be here? That is going to be about here. So there it is at 15. And the next one should be at 17.5. Cool. And the next one should be at 20. Oh, and of course that's when the thing ends. Awesome. Cool. So that's the kind of neat behavior that you can get. What I'm going to do between now and the next episode is look up some other interesting driving functions. But the last thing I want to do for this episode is create, you could probably already guess it, a phase space plot. I love phase space plots because they help you see how weird the behavior is being. So let's go ahead and let's see. We've got our G curve set up for the theta versus time. I still want to have that, but I want to add another display. So where do I get the here I get theta versus time. So for that, we want to call that G display. Let's make that one x equals 0, y equals 0. We'll keep that one in the same spot. And let's give that one a title of, that's going to be theta versus time. Cool. And then what we'll do is we'll do another one, G display x equal, let's see, my display, I want it to be right under the display that's over here. So let's make that an 800 and a y of, I think it's 400. We'll get it right below it. If not, I'll just adjust it. And we'll have the title be, let's do theta versus theta dot. That's usually the interesting thing. And then I need to make a new thing here. And this should automatically put this G curve in the most recent G display. That's my understanding of how it works. Theta versus theta dot. Actually, I guess it's more customary to put theta dot on the vertical axis. So let's move that dot. Here we go. And then what we'll do here is we'll say theta dot versus theta dot plot position equals theta comma theta dot. I sort of feel like we're doing our students a disservice when we say that it's y versus x, but when you give an ordered pair, it's x comma y. I don't know how to fix that, but I just feel like we're just doing our students a disservice for that. So theta dot vs theta dot vs theta. Just trying to cut off these typos before they have in theta dot. All right, let's give that a try. Okay, cool. I did get it almost in the right spot that I would want. Cool. So let's adjust that to the left by just a little bit. It's getting off the screen. Instead of 800, how about 700? All right, a little bit more. How about 500? Hey, there we go. Oh, all right, cool. Unfortunately, now this guy's getting covered up. Okay, so what I will do then is let's put the G displays first, and then we'll have the display up here so that it gets placed on top. 5. Hey, there we go, because you can still see the majority of the interesting stuff in here. So again, you can see where the push is showing up because it's showing up in this little discontinuity right here. So what you look for in an example like this is you're looking for some kind of what we call a limit cycle. Like, is there some, like it starts out up here, and it obviously doesn't say out there, but is there some pattern that it kind of zeroes in on after a while? So let's take out the T max for right now. While true, and let's actually increase the rate a little bit. Cool. So the question is there any kind of pattern that repeats? And it does seem to, right? So it seems to be repeating within this cycle here, and you can also see it over here where it's repeating itself. It's not really behaving like a sine or cosine because it does have this jagged discontinuity over here, right? So that's kind of cool. Let's put it back to the previous version that we had. Let's do, no, how do I do the comment out? Alt 3, of course. So let's do FD equals 5 cosine 6.28. You're getting tripped out by that thing up there, aren't you? Times the time divided by the period. There we go. I'll put back the sinusoidal one. Cool. And what we get here, we get probably what you would expect, what I hope you would expect, is more or less an ellipse because it's doing this cosine pattern, so it needs to be this nice, smooth, regular repeating thing. So you notice that discontinuity is gone because this one is nice and continuous. Okay, I think we can probably put a T-max of 100 on this thing. So what I might try to do a little bit later is instead of having this thing go for a maximum amount of time, instead of having this thing go for a maximum amount of time, would be to see if the code itself can find the limit cycle. Like, can it find where it's making this thing repeat over and over again and no longer has to worry about repeating itself, so it can just say, okay, I can stop now, I found the limit cycle. That would be kind of cool. Alright, so I think that'll do it for today. We're just kind of getting eased into this code. So next time we'll take a look at some more interesting driving forces, and we'll take a look, see if there's anything else we can do with the stopping condition for this thing so that I don't have to keep switching back and forth between different Tmax values. So thank you so much for watching. I will see you next time. Bye-bye.